There's a couple different types of solutions that we can actually go through with the Wright turbine. So here are the different types of eVTOL configurations that are currently coming out. You can see the helicopter on the far left-hand side. You can also see a lot of different other concepts that are out there as well. Everybody seems to be going for a different type of vehicle to see if it performs better than others. And really, it's because of those two different types of constraints that we spoke about in a previous video. There's the propulsion system. So most of these aircraft are using open prop designs. Only a few different aircraft are using a ducted design. One of them being Lilium. And John Liu on YouTube actually has a great series of videos that actually talks about the mechanics of the Lilium aircraft and whether it might succeed or not. And then the second issue that's facing eVTOL, the eVTOL community, is battery density. So making sure that we can actually have sustained flight for a set mileage or for a period of time for flying. So today, I just wanted to actually talk about vector thrust. You can actually see it outlined here on this particular slide. And the reason why I wanted to talk about vector thrust is because there's a very famous aircraft that's actually currently commercialized already by Bell Helicopter. It's the V-22 Osprey. So the V-22 Osprey, it's used in military configurations right now. And you can actually see this is just a cutout of the aircraft in terms of its support systems as well as the motor. But there's really three limitations that I wanted to talk about in terms of this particular aircraft. So whenever the aircraft is actually going from helicopter mode or taking off in a vertical lift formation and then transitioning into airplane mode, there are three gearboxes that actually induce a ton of stress to actually get that propeller spinning from 150 RPM, which is perfect for hover. And if they go any faster than 150 RPM, then you start to actually get a prop wash, or it doesn't actually sustain lift as well as it should, and it just chews up gas. And the reason why you move the prop into an airplane configuration is because all of that lift is being substituted by the wing spar itself. So that's the only reason why you actually move into airplane mode. So now you have this problem where you're actually taking the prop from 150 RPM to 2,500 RPM. And you have to move through three gearboxes to be able to actually get to that speed during the transition for flight. So, have you ever actually taken a bicycle wheel and spun it in your hands in a helicopter formation and then tried rotating it 90 degrees into airplane mode? The inertial force that it takes to actually make that bicycle wheel do that is pretty incredible. So it's not just the three gearboxes that are actually transmitting this power across this field array of RPM. It's also the inertial vibration or the inertial forces of actually getting that prop, that massive prop, to spin in helicopter mode into airplane mode afterwards. It's just a lot of inefficiency. And if you talk to a bunch of the soldiers that are inside this aircraft getting transported and actually feel this transition, they'll talk about the shudder of the aircraft during the transition of the blade, which is why a lot of the times they keep the motors themselves in a 45-degree angle, just because it's easier for them to actually make that transition with the aircraft in that mode. So the last limitation that's on this aircraft is whenever one of the engines is shot down, or whenever there's an inoperable engine, there's actually a wing spar, and you can see it as it goes from one engine to the next engine. It's a lot of complexity, but it's the redundancy that's necessary to keep the aircraft afloat. So whenever there's an inoperable engine, they actually feed power from the operable engine over to the inop engine to actually keep the airplane from crashing. It's a lot of weight to actually maintain that redundancy. So this is the Rolls-Royce engine. I've copy pasted it here. It's very similar to any other jet engine that we've been discussing. There's a central shaft that actually holds these fan stages during operation, and every single fan stage that's attached to that central shaft actually has a designated RPM. In turboprops, there's actually a gearbox between the front prop and the turbine itself. So the turbine is operating at a set RPM, but that's why there's the gearboxes, is to actually transmit that power from the combustions or post the combustion stage to the turbines and feed it back over to the prop as a way of actually maintaining that efficiency. However, it's just complexity. It's unneeded weight. It's completely redundant, and we could get rid of it in terms of technology through a direct drive system. So now we're going into the solution that I've discussed before with Wright One. We have a contra-rotating direct drive system. So very similar to what it is that you're seeing on the bottom left-hand corner over here. Uh, you see a more focused column of air. And that's exactly what Wright One accomplishes with our contra-rotating system. And it's direct drive because it's no longer connected to a central shaft. Every single fan stage operates independently. And the reason for that is that there are better, more articulate ways that we can actually access that power across the system. So think of the Wright One turbine going through the transition that a V-22 Osprey is going through. What we're able to do is we're able to actually tailor the RPM across every single fan stage. And the reason being for that is that if you have that same bicycle wheel and you rotate it with the right turbine, we can actually absorb that inertial load just by rotating a couple of the fan stages later on down the road at a slower speed to absorb it. It's like having multiple bicycle wheels in line with each other on the same hand, but they're rotating in different directions to actually keep the inertial load neutral. That's the power of the Wright turbine. So of course we have our videos here. There's the non-counter rotating airflow, and then there's the contra rotating airflow, which I've shown before. And then for the core technology, this is where we're going. We are developing the electric motor from scratch so that we can actually implement it as a cartridge system, so that you can actually tailor the performance depending on what it is that you need for your particular flight craft. Here are some comparables in terms of what it is that Wright One is looking to accomplish in terms of thrust over the next, looks like 4 years. So we're going to start with 500 pounds of thrust per motor. In 2025, we're going to be working to 2,000 pounds of thrust. In 2026, you can actually see some comparables in terms of PT6, the Catalyst, and then the FJ44. What we're looking to do is we're looking to get 30% penetration within the market for turboprops, regional jets, business jets, and advanced air mobility and eVTOL units as a way of actually decreasing carbon emissions by 500 million tons by 2030. And we see a path to actually make that happen. So here are a couple of technology contexts and key metrics that we're looking to benchmark ourselves across. We want to do propulsive efficiency, total efficiency, the product modularity, as well as for the fan stages and the core as a selling proposition. So for Wright One, we're looking to make this an e-commerce state. So we're actually selling the core on a website and providing key metrics and context for that particular core, and then have fan stages that we also sell on our website as add-ons, fixtures for that particular core. So if you're an eVTOL company that's developing a product, you might actually purchase the core and then one fan stage at the very beginning as you develop the motor or as you develop your airframe system. But then over time, you actually tune your particular core with additional fan stages that you can purchase through Wright One as a way of actually customizing the performance for your particular craft, depending on your airframe. So no longer do you have to depend on other turbine manufacturers going through an R&D development state and then costing you billions of dollars. And then on top of that, forcing you to sign service contracts as a way of actually recouping that money. No, all you need to do is you just need to go onto the Wright One website, purchase the core, and then slot in the fan stages that you want. And our software enables you to see the performance characteristic for your aircraft even before you fly. So what we've come up with is a modular, customizable, expandable platform for all eVTOLs. And we don't have to actually go through an R&D program or project that costs billions of dollars for one specific aircraft to be able to put it onto your airframe. It could be any type of airframe, as well as the fan stages that you could slot into each individual nacelle to be able to get the customized performance that you're looking for your craft. That's the uniqueness. That's the value proposition of Wright One. No longer do we have to have so much dedicated to one solution for one aircraft. Wright One has actually done all the R&D effort up front. And now we can actually just place it in terms of customizable performance across all eVTOLs moving forward.